Today, let us prove one of the most important theorems in group theory, Cayley's theorem. Cayley's theorem is named in honor of Arthur Cayley, a British mathematician who worked mainly on algebra. Cayley's theorem states that every group is isomorphic to a group of permutation. That is, the statement of the theorem is every group G is isomorphic to a group of permutations. We know that a permutation is a mapping of a set onto itself, and the mapping is 1, 1. So, here, to prove this theorem, we are going to prove that if we have a group G, we prove that this G is isomorphic to a group G dash, where this G dash, this one is a subgroup of the symmetric group SG. So, let us start the proof. Here we assume that G be a given group, then we define a mapping lambda x from G to G defined by lambda x of G equal to x into G for all G element of the group G. Now, we prove that this lambda x is a permutation on G. To prove that it is a permutation, we need to prove that this lambda x is 1, 1 and lambda x is onto. So, as a first part, we prove that lambda x is 1, 1. So, to prove this result, we consider lambda x A equal to lambda x B. This one implies, by definition, lambda x A is same as x into A. So, this one is same as x into B. We know that both x, A, B are all elements of the group G, and the left cancellation laws hold in a group. So, we have A equal to B. So, as a whole, if lambda x of A equal to lambda x of B implies A equal to B, means that the mapping lambda x is a 1, 1 mapping. And if we take any element C belongs to the group G, there exists x inverse C belongs to G such that lambda x of x inverse C equal to x into x inverse C. All x inverse C are all elements of the group G, and this one implies x into x inverse into C by the associative property of the group, and this one implies this one equal to C. So, corresponding to every C belongs to the group G, there exists x inverse C belongs to G, satisfying the condition lambda x of x inverse C equal to C. This means that this lambda x is onto. So, lambda x is a mapping from G to G, and this mapping is 1, 1 and this mapping is onto. That means lambda x is a permutation on G, or this lambda x is an element of the symmetric group SG. Let G dash equal to set of all lambda x where x belongs to G. Now, we prove that this G dash is a subgroup of the symmetric group SG. Clearly, G dash is a non-empty subset of the symmetric group SG. So, if we take any two elements of G dash, that is lambda x, lambda y element of G dash, then to prove the closure property, we need to prove that lambda x into lambda y is also an element of G dash. So, first we consider lambda x, lambda y operating on an element A, where A belongs to G. So, this one is equal to lambda x into lambda y of A, and this one is equal to lambda x into lambda y of A is same as the element y into A, and again lambda x of y of A implies x into y of A. X, y, A are all group elements, and since associativity holds in a group, we have x, y into A is same as x into y A. So, this is same as lambda x y of A for all A belongs to the group G. Lambda x into lambda y of A equal to lambda x y of A. This means that as a mapping, lambda x into lambda y is same as lambda x y. If x and y are elements of the group G, this one implies xy element of G by the closure property of the group. So, we have lambda xy is an element of G dash, and this implies that if lambda x and lambda y are elements of G dash, lambda x into lambda y, which is same as lambda xy, and this lambda x into lambda y is an element of G dash. That means closure property is satisfied in the set G dash. Now, to prove the existence of the identity element in the group G dash, we consider the element lambda E. Clearly, E is the identity in G, is the identity in G. So, if we have lambda x into lambda E, this one is same as lambda x into E. That is, we have proved that lambda x into lambda y is same as lambda xy. So, lambda x into lambda E is lambda x into E, and this one is same as lambda x. Similarly, lambda E into lambda x, this is also equal to lambda x. So, there exists lambda E belongs to G dash such that lambda x into lambda E equal to lambda x, which is same as lambda E into lambda x. That means this lambda E acts as the identity element in the set G dash. So, the identity element exists in G dash. Now, we prove the existence of the inverse element in G dash. That is, if we have lambda x belongs to G dash, this implies that this x is an element of G, and which implies x inverse is also an element of G since G is a group. So, lambda x inverse, this one is an element of G dash, and we know that lambda x into lambda x inverse, which is same as lambda x into x inverse, which is equal to lambda E. Similarly, if you take lambda x inverse into lambda x, this is equal to lambda x inverse x, which is equal to lambda E. So, we have lambda x into lambda x inverse equal to lambda E, which is equal to lambda x inverse into lambda x. That means the element lambda x inverse is the inverse of the element lambda x. Therefore, for every element in G dash, an inverse element exists in G dash. Therefore, this G dash is a group with permutation multiplication as the group operation. Now, to prove the Cayley's theorem, what we need is to show that the G is isomorphic to G dash. That is, we define an isomorphism from G onto G dash. That means, we define a mapping G from G to G dash by phi of x equal to lambda x. Then we show that this phi is a 1-1 mapping, then this phi is onto, and this phi satisfies the homomorphism property. Then it is proved that this phi is an isomorphism from G onto G dash. So, first we prove that phi is 1-1. Consider phi of x equal to phi of y. This implies lambda x equal to lambda y. This means that lambda x of A equal to lambda y of A for all A belongs to the group G. This one implies x into A equal to y into A for all A belongs to G. This means x equal to y by the right cancellation law. So, we have phi of x equal to phi of y implies x equal to y. That means the mapping phi is a 1-1 mapping. Clearly, corresponding to every lambda x belongs to G dash, there exists x belongs to G such that phi of x equal to lambda x. So, clearly this mapping is onto. Now, since we have proved that this lambda xy equal to lambda x into lambda y, we have phi of xy which is equal to lambda xy which is equal to lambda x into lambda y which is equal to phi of x into phi of y. That means the homomorphism property phi of xy equal to phi of x into phi of y is satisfied for the mapping phi. Therefore, phi is an isomorphism of G onto G dash, and so G is isomorphic to G dash. So, the proof of Cayley's theorem is completed because the theorem is every group G is isomorphic to a group of permutations. Here we have defined a group G dash which is a subgroup of the symmetric group SG, and all the elements of G dash are permutations, and we showed that our given group G is isomorphic to the subgroup of SG or the symmetric group SG. Hence, Cayley's theorem is proved. Thank you.